Good morning, everyone. Please take your seat. It's a great pleasure to give this lecture. I have not given a lecture now for almost a year because I had sabbatical, so I'm really looking forward to have this lecture and to discuss with you and engage with you in terms of research and teaching you something. Today we would like to just give you an overview of what the lecture is all about, and then we talk about how the lecture is organized, and in the end we will then start with a first small chapter so you see how things go. All right, let me start. Okay, I have to tell you that this lecture is actually recorded. We will put this on YouTube. We have a YouTube channel, and also on TIB. This is a public domain that also collects videos that are educational. So if you don't want to be seen, don't move here. If you ask questions, that's fine, because you won't hear it on the internet anyway. I will repeat your questions. But if you really don't want to be on the video at all, you have to tell me, right? So, all right. If I don't hear anything, you're fine with it. Good, let's start. This lecture is about non-equilibrium physics, and it will be focusing on two themes. One is stochastic dynamics, and the other one is field theories, and you will see how the two are actually connected. When you go back into what you have learned, I guess all of you have been to an undergrad course in thermodynamics and statistical physics. And here's a definition of what this is all about. But let me go through a few key things that I think are important in understanding thermodynamics, because they will somehow be the basis of the reasoning I have in this lecture. So there are thermodynamic variables and concepts which are quite important, and you might start thinking in your head, what are those important variables and what are those important concepts? So think for a moment. What would you do? What would be the key concepts, ideas, variables? Let me explain. There's variables, and you classify them according to being intensive or extensive, meaning scaling with system size or being independent of system size. And there are variables that are kind of well known also in classical mechanics, which is pressure. Pressure is something you can define in terms of force per area. But there are other quantities which are very particular and special to thermodynamics. One is temperature. Temperature is something completely outside the scope of any deterministic type of theory, where you would go to, I don't know, electrodynamics, classical mechanics, or quantum mechanics. There is no temperature a priori. So it's a genuine thermodynamic concept. And so are other quantities, like the chemical potential. That's also a mesoscopic quantity that makes sense only if you talk about a large system with a large number of degrees of freedom. For the extensive variables, there are also a few that have an obvious explanation in terms of classical concepts. Volume, of course, is just the size of the system. Energy is something you can define for any system you like. But once you go to an object like entropy, that's very distinct. And entropy is a genuine concept of a many-body system, and it's a concept that was introduced a long time ago when people were talking about heat engines. There's a range of potentials that derive from that. When you go to a classic thermodynamics course, you will learn about not only entropy, you will learn about the free energy, the Gibbs free energy, the Helmholtz free energy, and all these different quantities that you need in order to describe the macroscopic behavior of those systems. And then it's all about heat and work in the sense that you can actually make sense out of heat and work in terms of laws. And the way you phrase that is you first have to think about what is a thermodynamic equilibrium state. That's the first notion you typically introduce. That's also called the zeroth law of thermodynamics. And then you use the state functions to characterize the equilibrium state. And one really key law in thermodynamics are the various laws that you have that connect heat and work and also tell you what the thermodynamic equilibrium state is in terms of minima or maxima of corresponding free energy or entropy that you might have. And then, of course, entropy is not just an object that you need in order to characterize an equilibrium state. It's also an object which gives you information about how reversible or how irreversible a corresponding process is in nature. Okay, so far thermodynamic variables and concepts. The next question is, once you have this theoretical framework, what can you learn from that theoretical framework? First thing you have to realize is that a thermodynamic theory is a system theory. Don't really dig into the macroscopics of the system. You make macroscopic observations, and from those macroscopic observations, you infer laws. One of those laws are the equations of state. And the most famous equation of state that you learn in very early courses, even in high school, I guess, is the ideal gas law. And this ideal gas law, if you really think about it, it's an amazing law, right? It's valid for all gases, independent of molecular details, and it just connects pressure, volume, temperature, and particle number, right? And this is universal and applicable for, as I said, a wide range of different systems. Other equations of state are the van der Waals law for gases, etc., etc. So there are many laws that you can define. If you go more to the details of a thermodynamic system, like when you talk about interfaces and chemical potentials, then you have laws of the nature of what's called a Gibbs-Thomson relation and other relations that you might have. But again, they are inferred from observation. Right? They're not calculated based on some macroscopic model. They're inferred from data. So they learn from data, if you like. Then there are quantities which are quite key in order to characterize how a thermodynamic system responds to external perturbations. So like changing temperature, changing magnetic fields, changing electric fields, and those are called thermodynamic response functions. Like the susceptibility, the specific heat, and other quantities or compressibility. They play an important role, especially when you want to know how sensitive a system is. And as you might have learned, the systems are particularly sensitive when you go to a critical point. That means going close to a phase transition, where something quite fascinating happens. For second-order phase transitions, these susceptibilities diverge at the critical point, and then you have a switch in order from disordered to an ordered state, like a ferromagnetic state or a liquid-gas transition. The way you can describe those phase transitions, again, using thermodynamic concepts and not really so much a concept that uses statistical physics, is an idea that goes back to Ginzburg and Landau. And they have been arguing once you're close to a critical point, you can actually write the free energy in terms of a Taylor expansion of the order parameter. And then you just use symmetry arguments in order to infer what the structure of these free energies are. That's something I guess you don't really learn in statistical physics 1, but in statistical physics 2, that's quite a major theme. And then when you go off equilibrium, there are transport laws. We will hear more about transport laws in my lecture. The most famous one is the law of diffusion, where you have a current being generated by gradients in concentration, and the proportionality constant is the diffusion constant. There's other laws that are similar to that. They're called Onsager relations, and they connect the transport coefficients that you have in these various transport laws. Okay, so that's my one-slide summary of thermodynamics without any equations, but really explaining to you what the basic interesting concepts and laws are that you have for this type of theory. Now, there's this, you have to connect thermodynamics with microscopic physics. And I want to tell you a little anecdote. This little anecdote goes back to Robert Brown. I don't know who of you knows Robert Brown. He was a botanist, but he was the one who observed something super important. And I'll tell you in a second. So this is the story which you can find in the book by Charles Darwin. There he writes that before I took off on my voyage on the Beagle, I was visiting my colleague, and Brown, then his colleague, asked me to look through a microscope and describe what I see. Well, then Darwin was really curious what he saw, and I asked him what he has seen, but he didn't tell him. So he just told him, that's my little secret. But I revealed to you this secret, so here is the secret. This is what he saw. It's this irregular motion of particles that you have because the system is at a finite temperature, and this is just the expression of the heat energy that you have in the system. That's his little secret. He thought that this is actually due to some force which is necessary to give rise to life. Okay? And then he tried to come up with lots of different experiments to exclude this kind of hypothesis. And in the end, he found this is just a property of nature itself. It has nothing to do in particular with a living system. But nowadays, we really know that this Brownian motion is at the heart of statistical physics. And there is one of those three really famous papers by Einstein in 1905, where he writes about Brownian motion. And if you haven't read that paper, it's really, really beautiful. And it's very accessible because he introduces a lot of the concepts that you learn during my lecture in a very compact and neat form. And what he realized, and he had contact with Brown, is that there needs to be this irregular motion of particles because of the fact that the system is at a finite temperature. And as you might know, this then later gave rise to a Nobel Prize by Jean-Baptiste Perrin, and he got it for finding the molecular structure of matter in 1926. So this is the important point to make for a study of statistical physics. It's a different type of framework. Thermodynamics is a system-level theory. Here we're still interested in the behavior at a macroscopic level, but the way we approach it is different. The way we approach it, we try to figure out the macroscopic laws by using knowledge about the macroscopic physics, and on top of it, using probabilistic reasoning. Okay? It's not really calculating by brute force the many equations of motion that you have for your n number of particles, which is quite unfeasible. It's using ideas about probability theory that help you grasp and understand a complex high-dimensional system. All right. What are the variables and concepts? So same question to you. Before I tell you, you might try to figure this out for yourself. So before we had intensive and extensive variables at a macroscopic scale. Right now we go to the micro state. So the microscopic degrees of freedom that you have in your system. And then a key concept is that you use probabilistic reasoning to infer the macroscopic laws of physics. And I guess you've learned that, and there's many concepts that come with it. Ensemble theory, partition function, you introduce a interpretation of entropy, not as the state function that you learned in thermodynamics, but as a probabilistic concept that links the number of microstates to the entropy. And there are differences in how they are defined. Boltzmann used a different definition from Gibbs. The Gibbs definition is what nowadays is known as the Shannon entropy, and the Boltzmann entropy is just his constant times the log of the number of microstates. Now, fluctuations and correlations are something which is kind of new when you think about statistical physics, because fluctuations that are not something which are obvious to define in a macroscopic theory like thermodynamics. There you typically don't discuss that. The order parameter you can define also in a thermodynamic case, but it's much more enlightening to give a microscopic definition of the order parameter. And then a really key and important concept in the whole development of statistical physics was the renormalization group, because it helped us to really unveil how microscopic and macroscopic phenomena are connected over different types of scales. So what about macroscopic and mesoscopic laws? Of course, you have the goal to calculate now the ideal gas law, the other types of equation of state. So you can use this machinery to calculate these laws that you previously have just understood on a phenomenological level. But there's some new laws in statistical physics that are very, very inherent to statistical thinking. And the first one is the law of large numbers. And with it, the beauty of high-dimensional spaces. High-dimensional spaces look scary at first, but when you look closer, they have properties which are extremely useful. Right? For example, you learn in statistical physics that all ensembles are basically the same if you look at large enough systems. And that's because you have high-dimensional spaces in which the physics actually happens. Another law is the Boltzmann distribution, so e to the minus beta Hamiltonian. I put it down as a law because a real derivation of it is not really existing in mathematical form. Basically, you postulate it. Either you postulate the microcanonical ensemble or you postulate the Boltzmann distribution. But either way, this is something that you infer from nature, and a strict proof is, in my opinion, still lacking. There's theorems that are genuine statistical physics, like one is the fluctuation dissipation theorem. So I told you about the response function in equilibrium, like the susceptibility, specific heat, etc. In statistical mechanics, you can show that these response functions are proportional to variances in variables like the number of particles, the energy. So, for example, the specific heat is proportional to the variance in energy, the compressibility is proportional to the variance in particle number, etc. So, there's a deep connection between fluctuations on the one hand and response functions on the other hand. And that's known as fluctuation dissipation theorems. There's critical phenomena, so scale invariance and all that, and universality, which is really something you can only calculate if you have the renormalization group theory at your disposal, and you can infer from a statistical analysis and coarse grain over the different scales these kind of universal laws and scaling phenomena. There's concepts like linear response theory, where you can study how a system responds to external perturbation. That's kind of formalizing the theory of response functions to a statistical level. Yeah, and finally, emergence of irreversibility is something you can understand much better at the level of a statistical theory than at the level of a thermodynamic theory. All right, so that's again my one-page summary of statistical physics. Now, what we would like to do is to actually look into non-equilibrium physics. And for that, I give you here just an overview of the history of the field. And that's a rough overview. Don't take me here, by the numbers exactly and the details exactly. That's a very personal view of the history of the field. So from the 1900s to 1940, this was a phase where people invented stochastic dynamics. So concepts like the Langevin equation, Fokker-Planck equation, etc., they were invented at that time by people like Einstein, Langevin, Fokker, and Planck. Then from the 30s to the 60s, an important development was the development of linear non-equilibrium thermodynamics, so the behavior of thermodynamics close to equilibrium, but not quite. And the person that made really the most important contributions there was Onsager with his theory of coupled fluxes near equilibrium and the theory of entropy production. Then from 1950s to 1970s, these fluctuation dissipation theorems that I talked about were developed. Then in the years from roughly 60s to 80s, there was a first phase of classical theory of pattern formation, basically starting off from 1952 paper by Alan Turing, but then further developed by other people later on into a full-blown theory of reaction diffusion systems. From the 1970s on till now, this is still a very active field. People have developed field theoretic approaches. There's some names here, Doi-Peliti, formalism, and other formalisms. Basically, they are theories that give you a coarse-grained stochastic field theory, and they are applied in the wide range. They're applied for diffusion reaction systems, for critical dynamics, and nowadays also for systems far from equilibrium. I mentioned that already. This was a quite important development by Wilson, Fisher, and others. The renormalization group theory, where people figured out that you have scale-dependent behavior and universality in a large range of systems, including equilibrium systems, non-equilibrium systems, soft matter systems, etc. So now I'll list you a few things which are important nowadays. One range of phenomena people study is large deviation theory. And with large deviation theory, the idea is you study at a path integral level the statistical mechanics of events that are rare. And you try to characterize these rare events in terms of entropy production, and you also study fluctuation-induced transitions. The three fields that I'm going to focus on in my lecture is, on the one hand, non-equilibrium pattern formation. So that means we would like to understand how are systems organized in space and time, in systems that are stochastic, systems that are active, that means driven internally, and especially not those which were studied in the 1930s to 60s, so they were close to equilibrium. We would like to understand systems that are driven far from the corresponding thermodynamic equilibrium state. The next field is active matter systems. Those are systems, and I'll show you a movie in a second, that are composed of objects that are self-driven. These systems are off equilibrium because they break detailed balance. You won't know what this means for now, but I'll explain this later in the lecture what that means. And it applies to a broad range of systems, including some kind of self-propelled particles like bacteria or birds or fish, but also more relevant things like the dynamics of the cytoskeleton in a cell or flows that you find in the cell. And finally, the field of physics of living systems is something that has been gaining quite some momentum. And the idea is to use the laws of physics or even find new laws of physics by studying quantitatively the behavior of living systems like cells, bacteria, eukaryotic cells, organisms, organoids, all of that. Now, there's a lot of information. Now let me show you something beautiful. This is a quote by Plato, basically saying that you should always wonder about nature because it's fascinating. And here you see starlets over the sky of Rome. And you see how they self-organize into these beautiful patterns. Yeah?
What are these?
Starlets, birds.
What kind of birds?
Starlets.
Starlets.
Starlings, sorry, starlings. Stare.
Could you write it down on a... I don't know what this is.
Hope that's right. So for those that know German, that's Stare. Okay.
And this is real?
This is real. So you're exactly doing what Plato says. You wonder, this is crazy, right? This is absolutely fascinating, how they organize into these beautiful structures. And if you want to, look on the web, you'll find many, many, many different examples of that. Everybody who has a camera, I guess, when he sees that phenomena, will make a picture or a movie to just, look at it. Okay, so there is nothing that organizes this. There's no conductor leading the show and no conductor that made the choreography of all of that. This is self-organized by itself. All birds play the same role. There's no leader. And it's interesting to ask, how does that emerge, right? What's the laws of physics that give rise to something like that? It's not in the genes, right? This is not encoded in something which you would call information-based. Now, here are some other things that should make you wonder. This is yeast, budding yeast, so the stuff beer is made from. And budding yeast has to multiply in order to grow. And the way it does it is that budding yeast forms a pattern. So these are proteins that self-organize into a polar cap, like so. Okay, then underneath of that polar cap, and that's shown here, so you have here this polar cap, you have fibers, so-called cytoskeletal filaments. They organize into bundles, and these bundles then create forces that push out the cell wall to create a bud site. And thereby, these cells divide. Okay? So you have pattern formation in the form of these polar caps, structure formation in terms of these actin filaments, and then cell division. Another example is now a bacterial cell, E. coli. You have encountered, all of you have encountered E. coli, unfortunately. This E. coli bacteria is here about a micrometer typically in length. And what you see here is a pole-to-pole oscillation, again, of proteins that go back and forth between one cell pole and another. Why does a cell do that? Any guess? It needs to find midplane because it needs to divide in half, basically exactly in half. And there is no ruler that you have where you can say, okay, this is now half of the cell. Here I need to cut and divide. So the E. coli cell needs to find in a self-organized way a template, a pattern from which it can read off where midplane is. And this pole-to-pole oscillation basically creates a density profile that looks like so. Like in a pendulum, it spends more time at the turning points. So you have higher density at the turning points and a lower density in the middle. And that's where then another type of protein accumulates, so-called FTSZ polymers. They form a ring, and this ring then contracts and divides the E. coli cell at midplane. Again, this is a non-equilibrium process. It's far from thermodynamic equilibrium. It's driven internally by the ATP hydrolysis that goes on in all living beings. And that's the energy source by which this self-organized process is driven. Right? So again, it's cell division that the the purpose of this pattern that you see. Here, this is another organism. It's called a oocyte, so a basic form of a starfish. This is not the actual starfish here, right? This is just experimentalists squeezing the oocyte into the shape of a star, not for fun, but really in order to learn something about the pattern formation that goes on there. So here you see the patterns that form on the oocyte. They are very irregular, but when you look here at the beginning of the pattern formation, you see that there's kind of a wave that runs along the periphery of the starfish oocyte, and this wave of proteins is connected now to the morphology of the cell. So there's a linkage between the chemistry, the pattern formation, and the mechanics, the shape of that cell. And last but not least, there is an experiment by the group of Petraschwili here in Munich. So what she did is she used a lipid bilayer, it's basically a surface, and on this surface you have a pattern. You see this by this green web-like structure. And on top of this surface, she put a vesicle. A vesicle means an empty cell. A cell that has no interior, nothing inside, no DNA, no actin filaments, no motors. It's just an empty bag which is surrounded by a lipid bilayer. And this empty bag here shows a phenomenon that's very close to cell motion. So as you can see, it moves on the substrate here of the pattern formed by these green proteins that you see there. And that's a new field that's emerging over the last 5 to 10 years, which is called synthetic cell research, where people try to bottom-up construct properties that are cell-like or living-like with a minimal set of components that are much less than the actual huge number of components that you might have in a real cell. All right. So now, after showing you all that, let me give you another quote, which I find really key. It's Erwin Schrödinger's quote when he wrote this when he was in Ireland, escaping from Nazi Germany at that time. And he gave a set of public lectures where he himself, being the founding or one of the founding fathers of quantum physics, was studying, the question, what is life? And his view, I guess, after many, many studies of living systems is that he was just in awe of nature, saying, of course, when you look at nature, I don't expect the laws of physics to really change. There's still particles, there's still interactions, there's still forces. But if you look at the complexity of these systems, the complexity will bring about new laws. And these new laws will be distinct from the laws, based on the laws we have, but they will be distinct from those laws and form a part of physics in very much the same sense as all the other laws are part of physics. We have seen in thermodynamics the ideal gas law, van der Waals gases. We have seen Gibbs-Thomson relation, the law of thermodynamics, etc. And when you study complex systems, there's really a huge amount of new laws that are still not discovered. That means there's a lot of work for people like you to discover new emerging laws in living systems or complex systems. All right, with that, I think let me come back to this again. So non-equilibrium physics is what we study. It's systems that are driven far from equilibrium, far from the thermodynamic state. And what we want to do is we want to integrate ideas of system-level theory, so thermodynamic theory, and a microscopic statistical description in order to come up with laws that describe the transport, dissipation, the fluctuation, and all the emergence behavior across the scales. Here, this is just an overview over the themes. This is actually taken from my lecture notes, which are very detailed. So what we do first will be we talk about the foundation of stochastic dynamics in terms of random walks, elementary stochastic models, and what's called Markov processes and master equations. That's building the foundation on which we do the theory. Then we'll go on to study stochastic dynamics of particles, meaning we learn about Langevin and Fokker-Planck equation. We learn about how to simulate stochastic processes, and we learn about stochastic thermodynamics, so a theory that's based on a trajectory level description of the system and not a coarse-grained macroscopic description. That's, so to say, the basis. This is the application to particles. The third block then is we grow from discrete states to fields. And there I will show you how you actually construct, based on macroscopic models, field theories and the coarse-grained dynamics of those fields. And in the last part, we'll go to all these beautiful phenomena that are part of modern research. This is field theories of non-equilibrium systems. And here's just a short list of the things that I want to cover. It has those themes that I mentioned in my historic overview. It has non-equilibrium pattern formation. It has active matter theory, but it also has some more formal parts, namely the derivation of dynamic functionals, so field theories from the underlying microscopic models. I just wanted to flash by a few recent honors of people that have been working in the field. This is the set of Nobel laureates that we had in 2021. It's Parisi, Hasselmann, and Manabe, and they got it for different contributions. Manabe and Hasselmann basically got it for climate modeling, and Giorgio Parisi received the prize for the discoveries in disordered systems, especially his contribution to spin glasses and complexity emerging from randomness. So this really was a Nobel Prize honoring the field of stochastic dynamics and complex systems. Last year, I guess you all know, because that was everywhere in the news, the Nobel Prize in Physics was awarded to Hopfield and Hinton, and it's related to one field, namely Hopfield, work on networks, and that basically grew up out of his work where he tried to understand complex biological phenomena, namely neuroscience. And when you listen to one of his YouTube videos, you will learn that he was really curious about the complexity of nature and tried to find models that describe the complexity of neuronal systems. And that led him to the Hopfield network. And as we know now, this is the basis of associative memory models and has contributed a big time to understanding or to actual development of machine learning methods. And Hinton, he was honored for his pioneering work on deep learning and other things that are more at the level of algorithms that allow us to implement those machine learning methods. So machine learning is a problem in complex systems. It's something that was discovered by people that tried to understand complex biological phenomena. And nowadays, it's used everywhere. You use it, I guess, every day, basically, but it's not understood. And it's not clear why this works. Okay? It's used all over the place. Things are engineered at a rapid pace. New algorithms come up again and again and again, but there is no real deep physics-based understanding of why this all works. Right, and last, but by no means least, in 2025, so this year, the Boltzmann medal will go to two colleagues. One is Mehran Kada, who's working at MIT. And Mehran Kada really developed much of what we know about growth processes and systems that span equilibrium and non-equilibrium physics, especially the theory of interfaces. You may know the Kada-Parisi-Sung equations. That's one of his major contributions to the field. And Kuramoto, he works in Japan. He is known for his ideas on synchronization in complex systems, also revealing universal dynamic phenomena. So I would say this prize, again, stands for finding out what makes up emergent order in interesting non-equilibrium systems. So I have a teaching philosophy, and it's very important to me, these points that I'm going to mention now. One of my teaching philosophies is that I want this to be physics first. Meaning that I don't want to just put math out. I will try to motivate the physics questions, and from the physics questions, develop the concepts and the math that you actually need. Okay? And the focus will always be on the underlying phenomena of the system that we study. I want this study to be grounded in real phenomena, so nature as we observe it, because I really believe that physics should be a description of nature, not of mathematical concepts, but actually of natural phenomena. And when you do theory, I really firmly believe that theory has to be for concrete phenomena that you can observe experimentally. And that's why I focus on these kind of things. Third, the problem sets, they will be a core element of what we do here. If you just sit in the lecture, you will learn nothing. Okay? You actually will have to sit down and make the problems. If you do the problem sets, your chance of doing the final exam great is also great. There's clear statistics, there's clear evidence for that. There's a one-to-one correlation between your success in the problem set and the success in the final exam. Okay? But it's not about final exams, I hope, while you come here and study. It's really about learning the material. And I believe you can only learn it if you do it yourself. Okay? Listening alone is not learning. Okay? And we spend quite some time in actually designing those problem sets, so I hope you enjoy them. Fourth, I want to connect the material that I have in the lecture with ongoing research. So this is not a historic lecture about physics that happened a century ago. It's a lecture about physics that happens now as we speak, so to say. And I will point you towards interesting problems that you can study in a project during the semester, if you like, or in the semester break.